Good evening, everybody. You are all so welcome, and a special welcome to Katie Murley, all the way from the Netherlands. You are so welcome, Katie. I have a habit of just wittering on, but I'm going to hand over to you. Our screens and resources are yours for the evening, Katie.
Okay, well, thanks very much for having me. Maybe I'll go ahead and share my screen here. You can just let me know that it looks okay.
Yeah, that's perfect.
All right, great. Yeah, thanks. Thanks again for inviting me to give a talk. I'm indeed calling in from the Netherlands, not so far from Dwingelo, actually. And I'll be giving a talk today on the detection of ultra-high energy cosmic rays and neutrinos through their radio signals. So, in the topic of radio astronomy, but definitely more on the astroparticle physics side of things. Let's see here. Okay, so just to set the stage, I want to talk about how this all fits into the picture of what we're trying to learn. So we are looking for cosmic rays, which are ionized nuclei, and they can be produced in different types of astrophysical objects. Actually, we don't know exactly where they're coming from, and this is the point of studying them. But it's tricky because as they are charged, their paths towards on their journey from their origin to us are deflected in magnetic fields, and so we don't get to point back directly to where they come from, except for perhaps at the highest energies. Putting it in the context of multi-messenger astronomy a little bit, at a different source, at various sources, if there's enough dust and material there, cosmic rays can interact. I hope you can see my cursor here.
Yes.
Okay, great. Now my Zoom is covering it a little bit, but let's see here. Yeah, the cosmic rays proton indicated by P in this example can interact and produce neutral pions, which can then decay into the gamma rays, which we see. But above about a PeV or 10 to the 15 electron volts, gamma rays are often absorbed before they reach us. So they are a great messenger, but they don't work well in all energies. And then you can also have a situation where your cosmic rays at the source interact with dust, produced charged pions, which then decay into neutrinos, and that is the third multi-messenger that we're interested in. So this talk is going to be the first part focused on detection of cosmic rays. And then the second part at the end is I'm going to talk a little bit about how we detect neutrinos. And I also just realized here I have another example of how you can produce a high energy neutrino if you have a cosmic ray that's extremely high energy interacting with the microwave cosmic background. So starting out with cosmic rays. Just a little bit about the history here. We just had our 100th year anniversary of the discovery of cosmic rays. This is kind of fun how this happened. Victor Hess was looking at radiation. He had an electroscope which measures basically the ionization of the air, so how much loose charge there's floating around. And the assumption was that this mystery background radiation that he was measuring was coming from the Earth, something inside the Earth. And so to see if this was correct, he took this electroscope up in a balloon to try to prove that the further away you got from the Earth, the less radiation there was. But in fact, he saw the exact opposite. And so this plot here shows the amount of ionization as a function of altitude. And the higher you go up, the more radiation you measure. And so it turns out it was not terrestrial, but actually coming from somewhere else. And so this is the origin of cosmic rays or the discovery of cosmic rays. And it's also why it has the misnomer cosmic ray. It's not really a ray or radiation at all. They're particles, but it comes from this discovery. Then I'll go right to our current understanding of the cosmic ray population. So this crowded plot here shows the flux of cosmic rays, more or less how many cosmic rays there are at a given energy here. And there's a lot going on here. You can see it mostly follows a power law where there are many, many cosmic rays at low energies and very few at the highest energies. And we're talking about multiple cosmic rays per square meter per second at low energies versus one cosmic ray per square kilometer per year or even per century at the very, very highest energies. And so your strategy for detecting these things has to be quite different for probing different regions. So because at the low energies you have so many cosmic rays, you can measure them directly in a detector that is, for example, on the International Space Station. Your cosmic particle will go directly through your detector, so you can measure the charge, the energy, and you have a very good understanding of your type of particle that you're dealing with. And that is why in this figure you have the breakdown of all the different types of cosmic rays you can have. So hydrogen, helium, oxygen, iron, iron nuclei here. At the higher energy, you can't detect them directly anymore, and you have to detect them indirectly, which is what I'll talk about for the rest of this hour. And so it's much harder to get a handle of exactly what type of particle that you've seen. And so that's why at the higher energies, you just see a total population and not this breakdown of individual species. And just for reference here, what type of energies we're talking about. Here, 10 to the 8 giga electron volts is roughly where the center of mass energy lies for the Large Hadron Collider. So at the high end of the cosmic ray energy spectrum, we're really dealing with energies that we can't produce on Earth, and therefore also processes that we don't have a way to confirm that we totally understand based on controlled laboratory measurements. And then in terms of where these things come from, like I said, below the very lowest energies, we assume they come mostly from the sun, but above that, we actually don't know that much. What you do know is that in order to accelerate a particle to such high energies, you need to have strong magnetic fields or very large containment region of your particle. Um, Galactic cosmic rays towards the left-hand side of this figure are assumed in large part to come from supernova remnants. As they expand, they have shocks that accelerate outwards, and this is a good environment to accelerate particles. But this only works up until maybe PeV, and that's not even clear if that's possible. So this certainly cannot account for all cosmic rays. And then at the very highest energies, you have to get into the regime where you just have extraordinary magnetic fields or very large regions. And so you're talking about like the jets of active galactic nuclei, things like this. But this is based on an energetics argument and not on direct confirmation that they come from particular places. And then actually the region I'm the most interested in is this region of transition from galactic to extragalactic cosmic rays. It will tell us about the highest energy processes in our galaxy, and it's really just not clear what these can be. But some ideas, for example, are Wolf-Rayet stars, or maybe you have a cosmic ray accelerated by a supernova remnant that then gets reaccelerated in galactic wind termination shocks, just as a few examples. Okay, so what can we actually measure about cosmic rays and learn about them that tells us about our sources? Here on the left, I have a kind of a map of the the galactic magnetic fields here. So again, showing the difficulties in tracing back cosmic rays to their sources as they get scrambled. Um, we try to measure the energy that a cosmic ray is and also the type of particle it is. And the reason that is the useful information that we can extract is because of this relationship right here. And this is talking about the rigidity of a particle. Its capability to withstand magnetic field effects, more or less. So the maximum energy that you can achieve is proportional to the charge of your particle, a magnetic field at the source, and also the size of the source. So that's given as R in this equation. And so what this tells you is if you have a particular type of source, it's able to accelerate a proton to a certain energy. But then the protons will gain enough energy that they'll no longer be contained in the source and they'll escape. But for example, an iron cosmic ray will be continue to be contained in the source for longer, 26 times longer in this case, because of its charge. And so it can attain a higher energy. So if we're looking, this is kind of a cartoon figure here of the cosmic ray energy spectrum. If you're looking at the interesting features that you see here, it could be described by, for example, a source of cosmic ray accelerators that are losing their population of light particles here. And then at a certain later energy, they will start to lose their population of heavy particles. So the interplay between the charge, or equivalently the mass of the particles, which we call cosmic ray composition, as a function of energy, is the thing that can tell us about potential sources. Um, and I'll go back here for a second. You can see in this energy spectrum all of these features. For whatever reason, they're typically called the knee, the ankle. This is the toe over here, so they all are parts of a leg. But these are indications of a change in the spectrum, and then this is how we can interpret it as different sources falling off and taking over. So if this could be the end of the galactic sources, and then maybe another extragalactic source takes over here. We can also think about possible cosmic ray sources in terms of this famous relation called the Hillis plot. So this tells you about the size of the source, this x-axis here being the radius, and that in this relationship is this r, and the magnetic field strength, so B. And this kind of gives you an idea what possibilities are for accelerating cosmic rays to high energies. These diagonal lines indicate the energy where you would have to fall on this figure to accelerate a cosmic ray to a particular energy. And here you see 10 to the 20 electron volt protons. Well, basically all of our possible sources fall below that line. And if we look back here, 10 to the 20 is right where this cutoff is, in fact. And so um, we don't know if we just don't see cosmic rays above that energy or there's no possible source, but this is part of the mystery that we try to unravel. And then this picture here shows actually simulated trajectories of cosmic rays as they would arrive at the Earth. And you can see this red line is for cosmic rays of lower energies, and you can see the spiraling around in the magnetic field arms of the galaxy. And they really lose the directional information. But at higher energies, for example, these black lines here, the cosmic rays have a strong enough rigidity that they do get deflected a little bit, but they retain a lot more of their directional information. But there are many, many fewer of them, so this is the challenge. Okay, so then I'll move into a discussion of how we detect cosmic rays indirectly. And again, this happens via this cascade of particles that is induced when a cosmic ray primary particle interacts in the atmosphere of the Earth. And so this is called an air shower. And you basically have an initial interaction, which creates this whole cascade, millions or billions of particles, depending on the energy of your primary cosmic ray. And this can take place over kilometers, more or less, depending on the angles. If we look at, okay, so these red lines indicate a simulation of what an air shower might look like. So this is a full simulation where each individual particle is tracked. So each one of these red lines, for example, is an electron or a positron. I think the green lines in the middle are muons, but it kind of just shows you the trajectories of the different types of particles that you can have and how they might end up on the ground. And if you instead look at a schematic to see the different components of this air shower, you can see you get lots of different particles produced. In this example here, we have some pions. A neutral pion kicks off a cascade of electromagnetic particles, electrons, positrons, gamma rays. And you also have hadronic component, lots of muons reaching the ground, and also neutrinos. And these different components of the air shower can be detected in many different ways. For example, you can have particle detectors on the ground that see the particles as they arrive at the Earth. The electromagnetic component of this shower also produces sharp radio emission that turns out to be in the tens to hundreds of megahertz band, so ideal to measure with traditional tools for radio astronomy. There's Cherenkov emission, Cherenkov photons that can also reach the ground, and you can also kind of image the air showers that goes through the air with a fluorescence telescope. And we can also look at the total number of particles produced in an air shower. So what this plot shows is the atmospheric depth of the air shower. So 0 would be the top of the atmosphere. It's measured in grams per centimeter squared. So as the shower propagates, it goes deeper and deeper and deeper, passing more grammage. And then the x-axis shows the number of particles. And so you can see that at the beginning of the shower, you start with 1, and then the number of particles grows until you reach a point where you have maximum number of particles in your air shower, and we call that position X max. And then this dies out again. You also have a number of muons and then the hadrons as well. I just put a note here, air shower muons, an open question. Something interesting that we've realized in the last decade or so is that we don't understand the number of muons produced in an air shower very well at the highest energies. And this is because these air showers are taking place at such high energies that we don't have full confirmation of the models, the hadronic interaction models that kind of dictate the development of this air shower, which then produce the muons. And so some of the observatories see twice as many muons as they expect. And this is quite an interesting open question, actually. Okay, so again, what do we actually want to measure when we talk about the air shower? We want to measure the type of particle that initiated the whole thing, as well as the energy. So the energy is actually okay. If you can measure the number of particles on the ground, that's directly proportional to the energy that initiated the air shower. What's trickier is the composition. And the way that we try to get a handle on that is using this position called X max, which again is the position of in the atmosphere where the number of particles in the air shower is at a maximum. Um, and that is related to the type of particle that initiated the air shower. Protons having a lower charge, lower mass, will propagate on average further into the atmosphere before they interact with a molecule in the air versus a heavier cosmic ray, iron primary, for example, which has a higher chance of interacting earlier. And this plot here shows a number of simulations for both proton primary cosmic rays and iron primary cosmic rays. And on average, the whole air shower develops, oops, sorry, higher up in the atmosphere for iron than for proton, which is more fluctuating and also develops lower in the atmosphere. And so if you can measure this position, X max, for an ensemble of air showers, you can say on average whether you think you have a heavy population of cosmic rays or a light population of cosmic rays. And if you have many, many, many thousands of air showers that you've measured, you can even narrow it down better than that and say specifically, I'm looking at a proton population or a helium population or all the in-between elements. And so that is kind of more or less how this game is played. I also have a few simulations of air shower development here. So let's see if this will play. In these figures, it's going to show a number of different particles from the air shower, color-coded electrons in red, muons in gray. And this first plot here shows the atmospheric depth. And so even though these things are often drawn as this extended thing, it's moving relativistically as a kind of a pancake front as the air shower propagates towards the ground. So when your particles hit the ground, it's like all coming in one wave. If we look at what a different air showers might look like for different types of primaries and for different energies, this shows simulations of an air shower for a PeV 10 to the 15th electron volt photon, proton, and iron. And so the heavier primaries kick off an air shower with more particles, which makes sense. Um, and the gamma rays, the photons, are much smaller. And this is actually very useful for ground-based gamma ray observatories to distinguish between hadronic showers, protons and iron and everything in between, and gamma rays, because the shape is very different. So these are for same energy, different types of primary particles. If we look at different energies, same type of primary particle, you can see that at lower energies, you have many fewer particles in your air shower. You can see some kind of clumping and interesting distributions here. And the higher you go in energy, this all kind of washes out and you have a more evenly developing cascade. Okay, so here are a few examples of different cosmic ray detectors around the world, all using different techniques. Cascada Grande was one of the major players a couple decades ago and really helped kick off the field in the modern era. This is at the campus at Karlsruhe at KIT, Karlsruhe Institute of Technology. And you can see all these little white houses here are housing particle detectors. Um, Here is an example at the South Pole ice top. You might know the neutrino detector ice cube. I actually have something to say about that a little bit later, but this is a particle detector on top of that neutrino detector, which acts as a veto. Tunka is in Russia, and here you see a radio antenna and a couple Trenkov detectors. Hawk is a gamma ray observatory that looks for Trenkov photons on the ground, and each one of these tanks is filled with water and detects gamma ray and cosmic ray particles as they pass through. The two biggest observatories are called Telescope Array. This is in Utah in the United States, and you can see this is a scintillator panel here. Um, to observe high energy cosmic rays, you have to have huge detectors. And so both of these two are just gigantic and have spacing in between their different scintillators of a kilometer or so. And the Pierre Auger Observatory in Argentina. And then what I work on most of my time is LOFAR. In the Netherlands, this is, if you're familiar with radio astronomy, I guess you probably know LOFAR and the Super TERP. And it turns out to be a brilliant cosmic ray detector, even though not at all designed for that purpose. Okay, so I'm going to now focus on the radio emission from air showers, where it comes from, and how it can be used for reconstruction. So this is very analogous to Cherenkov emission. When um, when your particle cascade is moving, it's moving faster than the local speed of light, which means it can produce some kind of Cherenkov-like effects, where radiation from all different parts of your shower can arrive at a particular position on the ground coherently. Now, why is there radio emission at all? That has to do with the fact that in this air shower, you have many, many electrons and positrons. And as these particles are passing through the Earth's magnetic field, they feel the Lorentz force from the magnetic field, and so they separate in opposite directions. And so you get this kind of moving current developing with your air shower. And because you have a changing current moving at the speed of light, you get a very sharp radio pulse. This emission is polarized in the direction of the geomagnetic the V cross B, so the Lorentz force direction here, and it's linearly polarized. You also get an effect from the fact that as your air shower passes through the atmosphere, it kind of kicks extra electrons into the air shower. And so you also have a growing negative charge in your shower. And so this also emits coherent radio emission. This one is linearly polarized, but in the radial direction. And so the combination of these two emission mechanisms gives you a very interesting pool of radio light on the ground. So what this figure is showing here is the energy fluence, basically the strength of your electric field on the ground. And you have positive interference on this side of the shower from these two adding up together, and you have negative interference over here. And so this gives you a very unique pattern that you can then use to do some event reconstruction. Just a few simulations of what this signal actually looks like here. So this is the electric field that you could measure with an antenna at a position here in your radio footprint. So it's very sharp peak in the time domain here. We're talking about, a few nanoseconds wide signal, and very broad in the frequency domain here. If you move to a different position here, let's say you put your antenna a little bit closer to the shower core, you lose a little bit of the coherence of your signal. So now your electric field is spread out more in the time domain, and you can even see some interesting interference patterns popping up in the frequency domain. I actually don't know where these come from. I have a master's student right now who's doing an investigation to see how this air shower is creating this interesting interference pattern. And if you have your antenna in the outside of the radio footprint, you also again start to lose your coherence a little bit and have loss of strength of your signal in the higher frequencies, but still coherent signal at the lower frequencies. Okay, so what do you learn? How can you use this information to reconstruct what you need to know about your cosmic ray? Um, the electromagnetic energy of the air shower is basically all converted into these electrons and positrons, which then produce this radio emission. So you can reconstruct by integrating this pool of light on the ground your shower energy. The hadronic uncertainties in the air shower development that are a big problem for particle detection at the high energies actually don't factor in so much here because we're talking about electromagnetic particles, which can be just understood using Maxwell's equations. And then the shower development, in particular, this position of Xmax, can be reconstructed because the pool of light is heavily dependent on how far away your air shower is developing. So you get a little bit of a different pattern on the ground if you have a shower developing farther away. You can picture like a flashlight being held further away from the earth or closer to the earth. This was actually the first detection of an air shower using radio techniques at General Bank in 1964 here. I this is really fun because it's actually the same technique we use now. So what they did was they had a particle detector for detecting that an air shower occurred using Geiger counters actually here. The reason for that is because it's tricky to excuse me, it's tricky to trigger on a cosmic ray using radio signals alone, just because of the radio backgrounds. It's there's background RFI radio frequency interference all over the place, and so it can be tricky. But particle detectors provide a great method for triggering radio readout. So what they have here is an antenna setup. It's, I guess, not really obvious here in this darkened area in this field. And then they have a readout of this antenna on an oscilloscope here, and it's just triggered using this Geiger counter. And there's also a camera that's triggered to take a picture of the signal on the oscilloscope and the timing. And this was the first indication that radio emission was indeed produced from cosmic ray air showers. We do something similar right now at LOFAR, actually. And so I'll talk now about some modern experiments that we're using to probe different parts of this cosmic ray energy spectrum. Um, the size of your detector, the amount of area basically you've instrumented on the ground, tells you which part of this energy spectrum you can measure in. And that's because the footprint of the event on the ground, both radio and particle, grows with energy. So if you have cosmic rays in this region, you can be talking about kilometers, and so you need to be able to measure coherently over many kilometers. In this transition region between galactic and extragalactic sources, you're talking about a square kilometer or so, and that is like perfect for what we can do with LOFAR. So that is indeed what we do at the LOFAR Superturp located in the northern Netherlands. This is a figure, kind of a mapping of how our detection method works. LOFAR has low band antennas that we use. So these measure in the 30 to 80 megahertz bandwidth, simple dipole antennas here. And the nice thing is that there are just so many of them. Typically, if you were designing a cosmic ray experiment by hand, you would, maybe typically you measure a radio footprint from an air shower with maybe 5 antennas. And at LOFAR, because these are just pre-existing, we can measure it with hundreds of antennas per event. This map here shows the location of different LOFAR antenna stations. So you have the Super Terp here with many, many antennas, and then a few satellite stations here. The boxes in this figure show the position of particle detectors that we have located on the ground, and these again provide a trigger for the radio readout. So the antennas are each buffered for 5 seconds. As your air shower propagates across the Super Terp, the particle wavefront reaches some subset of these scintillators, and then we collect this information in real time, see if, for example, 12 out of 20 or something has seen a signal, and then send a trigger to read out the radio buffers at LOFAR. This is a picture of our particle detector, not so much to see because it's all shielded in a box there, but this is what it looks like schematically. What we have is 4 panels of scintillator plates, which are 3 centimeters thick, and wavelength shifters to catch the photons from each of these panels, which then feed into a PMT here. And this is all shielded in a metal box, so it doesn't cause any unwanted radio backgrounds at this sensitive radio telescope. These are just a couple examples, cosmic ray data actually, of what our raw signals look like. So we really require time domain voltages. Nothing has been beamformed or channelized or anything like this because we just need voltages on the nanosecond timescales here. Okay, so this is actually a picture of a figure of an event. This is the data that has been collected by our particle detectors. So again, that would be these 20 blue points scattered across the superturb there. So what you can see, we do, I mean, it's mainly used for triggering, but we also can do event reconstruction. This first panel shows the time of arrival in each of the scintillator panels indicated by the size here. So you can kind of see the event sweeping across the superchirp. The deposited energy here, this panel in particular has highest, I don't think I mentioned this, but the number of particles falls off radially from where the shower core goes through. So if you're closer to the shower core, you have many more muons, electrons, etc., passing through your scintillator compared to as you go farther away. And this allows you to reconstruct the energy of the air shower. This whole curve would move up or down depending on the energy. Oh, this is a visualization of how the radio antennas now see an air shower. So the color marks the strength of the radio emission. So this yellow spot in the middle is closest to the core. But you can see that you get this, yeah, compared to other cosmic ray experiments, very detailed sampling of what your radio footprint actually looks like. And here are a few simulations. Well, okay, sorry. Here are a few events that we've measured and a simulation in the background to kind of show how the event reconstruction works. So what you're looking at here, again, it's a picture of the superturf. The colored points here inside the circle show the antenna positions, and the strength of the color shows the measured data. And then what we do is we run simulations and try to match them to what is measured here. And the simulation then gives the full picture of the air shower and then allows us to say what type of particle we saw. And so if you look at what we reconstruct, which again is X max, this point of maximum particles in the air shower, um, you see that it's changing. If you have all proton, you end up on this red line here. If you have all iron cosmic rays, you end up on this blue line here. And these are all different cosmic ray experiments, and the LOFAR points kind of are in the cyan color. You can see that the population is moving from light to heavy to light to heavy again. And that's again indications of different sources. So we expect this is the end of the galactic cosmic ray population, the onset of the extragalactic, and then back to heavy. We also are really looking forward to doing these measurements at the SKA. I mean, if LOFAR is already the most sensitive radio instrument for detecting cosmic rays, so SKA is going to be amazing. Here's a comparison to what we would measure now. These are, again, the antenna positions at LOFAR. If we picture the same event at the SKA, you just are getting this complete coverage of the radio footprint, and we're going to be able to learn so much about air shower physics and development there. We also, at the SKA, the square kilometer array, will be able to measure in a very wide frequency band. And another interesting thing you can do is look for these irregular showers which develop in the atmosphere. It can happen that, for example, if you have a helium cosmic ray, your particle interacts in the atmosphere and fragments, and then you have kind of two showers developing on top of each other, and it can create these like double Cherenkov rings, which are going to be very interesting to study. Just for comparison, again, here's a simulation of what we would expect a cosmic ray event at the SKA to look like. So we're very, very excited about the next decade of observations there. We're also putting a particle detector at the SKA. Here, there's already There is already a prototype at the Murchison Wide Field right here. This is difficult to manage in the Australian temperatures because you have wild temperature fluctuations, which are going to greatly affect the sensitivity of our silicon photomultipliers to the signal. So it's going to be a challenge, but we are actively working on this so we can do cosmic ray detection at the SK. Finally, I want to mention for the cosmic ray side, at least, the Pierre Auger Observatory. So this is this huge cosmic ray observatory in Argentina. You can see here it stretches 70 kilometers on a side, and this is measuring the very highest energy cosmic rays. Um, there are a number of different detection techniques that are used in conjunction here. One is this fluorescence telescope. That's what all these four colorful points are here. They kind of map out the development of the shower in the atmosphere. These points on the ground are Cherenkov detectors to detect particles, and we also have radio antennas. So here's a picture of one of the Auger detectors. Each one of these is one of these white points here. So water Cherenkov tank, also a scintillator on the top here, and a radio antenna to get the full picture of the air shower. There's actually a little cartoon here also of what it looks like to measure um, at Auger. So now you get a feeling for the spacing of the particle detectors compared to the particle shower footprint on the ground. And then this is what the data collection in the water tanks actually looks like. You have PMTs, photomultiplier tubes here, always on. Your air shower particles come into the water and produce Cherenkov photons, which can then be measured in these photomultiplier tubes. And then coincident events are searched for from among all these different stations. This is a picture. This is like a beautiful event that was seen with those radio antennas that were actually only recently installed last year. This is a super inclined cosmic ray event. It's almost skimming the Earth, so it's coming in like almost completely at ground level, and it's stretching over 60 kilometers. So this is just, I mean, I don't know how it looks when you don't see these all the time, but we were looking at this and just, staring at it and marveling at it because it's such an amazing thing to see something so huge and horizontally propagating. Now, what has Auger actually learned? So cosmic rays at the lower energies, again, don't say much about their sources because they're too bent in the magnetic fields. But at Auger, we're dealing with energies that are high enough that you actually can start to do a little bit of pointing on the sky because they're not as bent. And so Auger does see this hot spot on the sky. It sees more cosmic rays coming from one direction than the other direction. And this is a galactic coordinates here. And so actually there are fewer cosmic rays coming from the direction of the galactic center at the highest energies than coming from outside, which is kind of interesting and also an indication that these very high energy cosmic rays are extragalactic. There is an overdensity from the Centaurus A galaxy. It's not like discovery level yet, but we're getting to the point where we're almost confident to say that some population of these high energy cosmic rays are indeed coming from Centaurus A. Interestingly, if you do a complete mapping to all the AGN, active galactic nuclei, you don't see such a strong correlation. So that's could be something to do with the fact that that's relatively close. Starburst galaxies are also showing an increasingly strong correlation with the arrival directions of cosmic rays above 8 exa electron volts. But if you look at the very, very highest energy events that we've ever measured, so this is the sample of the very highest energy cosmic ray events, they don't all point back to one place. It's still not clear where they're coming from. And so this could be a lack of our understanding about extragalactic magnetic fields. They could be from transient sources and not some kind of steady state galaxy, something like that, or exotic physics. So this is all something to be determined in the future. And Auger was just upgraded with a lot of different equipment that will allow it to do better reconstruction. So hopefully we'll be able to figure this out in the future. All right. Now, in the last part of this talk, I just wanted to tell a little bit about the complementary techniques that we use to actually measure, or try to measure, I should say, ultra high energy neutrinos. These are neutrinos that we expect to be from the same sources as these ultra high energy cosmic rays, or the ones that can be created when a ultra high energy cosmic ray interacts with cosmic microwave background. Again, these haven't been measured yet, but since we see the cosmic rays, we know that if we understand everything, these neutrinos should exist. Now, the problem with neutrinos, of course, is that they are neutral particles and so rarely interacting. And so that makes them tricky to measure. I like this figure a lot. This shows the galactic plane and different types of light and particles. So you have optical, you have gamma rays, and now in the last couple of years, the galactic plane has also started popping up in neutrinos. So if you say that all of your cosmic ray sources are also neutrino sources, you could maybe make an educated guess that these come from the galactic plane, and so you would expect a neutrino population to look like this. And then this is what has actually been measured so far. So again, it's just the early days, fuzzy images, but we are starting to see the galactic plane pop out from these neutrino searches, which is exciting. This plot here shows the flux of neutrinos. There's a lot going on. But broadly speaking, this y-axis here again shows the flux, the number of neutrinos for a certain space for a certain area and time as a function of energy. This blue and red line is what we have measured so far. So around a few PeV, a few 10 to the 15 electron volts is the highest energy that we've measured, but we do expect this population to continue further. And so we really expect cosmic rays in this region to exist. So far, the most sensitive neutrino detector at the high energies is IceCube. And this is this massive detector buried a kilometer beneath the ice at the South Pole. So what you're looking at here is the South Pole Station. They've drilled many holes, and then on each of these holes are optical detectors here that kind of instrument this whole volume. And what they hope to see is if a neutrino is passing through the ice, it has a chance to interact. Again, most will not interact, but now and then it just does by chance. And the neutrino will produce a particle that will make a signal. So, for example, an electron or a muon will be generated with a high fraction of the neutrino energy. That can pass through your detector and then create Cherenkov photons that light it up. So this is an image of what that looks like. You see the color shows the track of this neutrino-induced cascade through the detector. If I can play that again here. The color is the timing. And so you can see it starts on one side and goes other, and this is the neutrino track. Also interesting that it's coming from the downward to upward direction, which means it's traversed a large amount of Earth actually before it's entered the detector, which is also a good indication that it's a neutrino because other particles aren't traveling through the Earth. Very interestingly, I think it was last year, KM3 Net, which is another neutrino observatory that's still in the process of being built, discovered an extremely high energy neutrino event, approximately where this red line is. So an order of magnitude above anything else. This was very interesting because this detector is not fully built, so it's extremely lucky that they saw such a thing. This is also a very cool detector. It's a similar concept to IceCube, but rather than being put in the ice, it's buried under the Mediterranean Sea there. But the problem with both of these detectors, for the high energies at least, is that they just do not have enough volume, instrumented volume, to reach the highest energies. And that is because they use optical detection. So this is a picture of one of their optical receivers that sees these Cherenkov photons that are scattering through the ice or the water in the sense of KM3 Net. Um, Optical photons won't travel much more than the volume of something like IceCube. So square, here you can see the relative size of that. If you could build a detector that looks for radio, signals from these cascades, you automatically instrument a much larger volume because radio waves propagate much further in ice. And so that is the concept of trying to use radio waves rather than optical photons to detect cascades in ice. Now, yeah, spoiler alert, we haven't detected anything yet, but there's a major push, and this event from KM3 Net is giving us a lot of hope that we'll be able to see something soon. So conceptually, how does this work? We saw earlier the air showers. You have an interaction in the air, you produce your air shower, it develops over 5 kilometers or so. In the ice, you have an analogous situation. You have your neutrino inducing a cascade of particles. It's developing in a dense medium, so it's much shorter. It only develops over 6 meters or so. So that changes the radio emission to higher frequencies, but it produces a Cherenkov cone of radio emission, which again can travel for kilometers or so before it's attenuated. And so this allows you to instrument a very large volume of ice with very few antennas. Yeah, and this just shows that the frequency range, we're talking about hundreds of megahertz here, rather than the tens to hundreds of megahertz for cosmic rays. There are a number of efforts ongoing to try to pull this off. Anita is a very interesting one. The idea here is that you have a balloon with many antennas that are kind of scanning the surface of the continent of Antarctica. This is actually the project I worked with on a decade ago when I was a PhD student. They've actually seen a number of ultra high energy cosmic rays, but no neutrinos yet. ARA is an effort, what does it stand for? Ascarian Radio Array to instrument the South Pole. GRAND is an interesting idea where you cover a mountainside with antennas and you look for a neutrino interacting in a mountain and producing a cascade that's kind of escaped the mountain. And there's another number of other efforts that make use of the same types of ideas. I'm going to talk today about RNOG, which stands for Radio Neutrino Observatory Greenland. Um, this observatory is located at the very apex of the Greenland ice sheet. It's the highest point on the continent, even though if you're there, there's no features. It just looks like flat ice. But if you look at a map of the altitude of Greenland, it's actually quite high. I believe it's 3 kilometers high. Um, Okay, and so Greenland is chosen for a few reasons. One is that they have very cold ice, which is good. It makes it reduces the attenuation of radio waves. And also just logistically, it's very challenging to do anything at the South Pole because everybody's trying to build experiments there. So Greenland is relatively accessible in that way. And there is a facility run by the NSF from the US that hosts different types of science projects at Greenland. Um, Here you can see there's very little infrastructure there. Here you can see what's known as the Big House, and this is the major hub where people work and eat and watch movies, things like that. There's about 30 people, 35 people that live and work at Summit Station at the peak season in the summer. Most of them are not scientific staff, but keeping the place operational. And in the winter, there are 4 people that usually stay over, and it's quite a thing because it's complete darkness from late October to sometime in the spring. And in the summer, you have 24 hours daylight. This is a picture of a map of the facility. It actually changes every year because all these buildings are on skis and they move around, except for the big house, which is on stilts because it has to be raised every couple of years because of snow accumulation. A couple interesting things. This is a skiway where you have to bring in all the people and materials, and it's really just ice. And so the planes land on skis and also have to take off on skis. And then yeah, this is another the picture of the big house here. And then there's a few like this is mechanics, birthing modules where people sleep, things like that. So the concept here, this is a schematic. The idea is that you have antennas on the surface of your ice and also buried deep, 100 meters deep. And so when your neutrino is propagating in your ice, interacts, you have a couple different paths for the radio signal to reach your antenna. This is because there's a gradient index of refraction, so that can help with reconstruction. This is a schematic of what each of these stations actually looks like. So you drill a hole 100 meters deep. You have some vertically polarized antennas and some horizontally polarized antennas and some LPDAs on the surface. All of these different polarizations, again, help for reconstruction. You also have calibration pulsars on here, which can help you locate the actual positions of your antennas in the ice because you tried to put them at 100 meters, but it's tricky to get it exactly right. And here's a couple pictures of this experiment being deployed. So I think this is a video. No, okay, it's not a video. This is a snow truck, for lack of a better term, that is pulling around the drill that is used here. Actually, it's kind of interesting. It never is usually above 0 degrees in Greenland at this at Summit Station, so it should always be frozen. But the way the drill works is it kind of digs out chips of ice in 10-meter segments. Here's actually an example of one of these ice chips. And if you have this metal drill and you have the sun beating down on it, it can actually melt and create a whole problem for you. Um, you can't basically empty out your drill. So they had to build a white tent to actually cool down this drill. And this is what the holes actually look like. They're like 20 centimeters or so wide in the end. And this picture of ice actually is from the bottom. So I think this was, as you go deeper in the ice, you're actually going back in time because of the snow accumulation year after year. So I think we decided this was a few hundred years old. And then you can put this in your drinks and it sizzles because of all the bubbles in the ice. It's pretty fun. The deployment of the stations looks like this. This is a portable hut that is dragged around on a snowmobile here. And the idea is that we use this to deploy the instrumentation and keep our fingers warm because the conditions can be quite nasty outside. So here's a picture of antennas being deployed down a string. We have a pulley system again because it also becomes very heavy at some point. And so you pull your hut over the hole that's been drilled and you align it, and there's a hole in the bottom of this hut here, and so you can do all of your instrumentation work in a nice temperature. Now, we haven't seen this was the concept was actually started in 2019 by a group of people who are working on different related experiments. And so it was only the first stations were deployed in 2021. And then every year a few more stations are deployed, and I think it's up to 9 or so. And while we haven't seen a neutrino yet, we have seen interesting sources which can help for science validation. So, for example, this is a solar flare that was seen 2 years ago in the surface station and the 100-meter deep station. So this is a radio signal from a solar flare. And you can also track airplanes as they go overhead. So these are points where airplanes were sparking or something like this. And you can track as they travel overhead of Summit Station. And then this is the final slide of R-No-G. This is what it looks like when a station is complete. Everything is buried under the ice. These red flags mark where the holes are in case you ever have to try to find them again, but it becomes harder and harder every year as things become buried. This black box here is hosting all of the instruments, and it's sent back to the big house via an antenna here. And these are solar panels which keep everything operational, but only when the sun is up. So this is only operational half the year. There are a lot of efforts ongoing to try to use wind turbines as well, but those are very tricky because for one reason, they make a lot of radio background noise as they spin, which is causing a problem for this experiment, which is triggering on radio signals. And also they get jammed very easily in stormy weather, which there is quite a bit of in the winter here. So these are the different station positions which will eventually be deployed. And so far we've done this collection here. So every year a few more are checked off the list. And with that, I will just say the future of radio detection of cosmic particles is bright, I think. We have a lot of different ongoing projects, and the next decade, I'm convinced we'll see a neutrino and kick off the cosmic ray detection at the SK as well. Thanks.
Thank you very much, Katie. Yeah, that was just excellent. Um, are there, yeah, Ted's floating up a
Very good. Well done. Thank you.
yeah,
Thanks.
yeah, most excellent. Um, oh, Diane, you got your camera working. Um, are there any questions for Katie?
Yes. Me? Can you hear me?
Yes.
Oh, good. Katie, thank you. Very good presentation. Are there any known effects with regards to atmospherics and interaction between the particles when they enter the atmosphere? For example, do you get, let's say, a smaller burst if the atmosphere is thin or thick, for example?
Yeah, indeed. Maybe I can. Whoops. I stopped sharing. I'll just go back to a picture of this air shower here. It does depend on the atmosphere. And so what we do when we try to do event reconstruction is we often simulate a particular atmosphere on a given day. But another atmospheric effect is actually the angle with which the particle enters the atmosphere. So if it's very inclined, the the cascade is developing higher up in the atmosphere, and so the entire thing is much more stretched out because it's passing through less grammage, and that definitely changes what the signal looks like on the ground. Also, the number of particles on the ground. So if you have a vertical air shower coming down direct, um, you have many muons and electrons in your air shower, and both reach the ground. But if you have a very inclined air shower coming in like this, most of your electrons are absorbed, and then you only have muons left over at the ground level.
Yeah. So it basically it's the angle of attack, as it were, gives you a different shower every time.
Yeah, yeah.
Thank you.
And
Yeah,
how frequent are these air showers? How often are they occurring?
It depends on the energy. So, around PeV, you're talking about 1 per square meter per day. At the very highest energies, 1 per square meter per century. Very rare. So it really, really depends on the energy, and that's why experiments that probe different energy regimes have to have such a different strategy. That's why Auger is so huge, is because it has to be 100 square kilometers, or you would never see anything. So.
yeah. You made a rather cryptic remark about the muon flux at various stations being anomalous. Are you able to elaborate on that a bit?
Sure. This was, oh, I don't think I have a figure, but this was what has been measured at Auger. And this is a problem at the very highest energies because up to about 10 to the 17 electron volts around this point on this plot, um, we can confirm hadronic interactions, which is what is guiding the development of the air shower. This can be confirmed in a lab, and basically the hadronic interaction models, which are used in simulations, can be tuned to reality. But at the high energies, you have to extrapolate your models that are used for, simulations, which are then used for the event reconstruction. So what Auger found at the very high energies was that given what the rest of what they knew about the air shower, the electromagnetic component, the energy, the arrival direction, they couldn't match the number of muons detected with what could be simulated. And this was noted and published, and then a number of other experiments also confirmed the same discrepancy. And it's something that grows as a function of energy as we have less and less knowledge about, or I should say, as you have to extrapolate more and more from hadronic interaction models that can be tested in a lab.
Thank you.
Is there an upper energy level at which interactions with the cosmic background radiation photons would just essentially absorb all of the particles that would be at that energy level?
Yeah, indeed. I didn't mention this, but there is a limit. It's called the GZK limit, acronym for people's names, which I'm forgetting right now. But it's interesting because that limit is basically right here, which is where you see this cosmic ray cutoff. But it's not clear yet whether that is what is causing this energy cutoff, or if this is some kind of natural cutoff from what accelerators are possible to achieve. So right now, this
Oh,
is, yeah. Yeah, so right now this is one of the big open questions. Um, I could say maybe that something that would point to this cutoff being the place basically where all your cosmic rays are getting absorbed would be if you had a lighter cosmic ray population at the high energies, because the protons are what is interfering with the cosmic ray microwave background, and then forcing this cutoff. But actually, we see like a heavier population of cosmic rays here, so it's a bit of a mystery. But that point would be right around 10 to the 11 GeV.
And at those extremely high energies, do relativistic effects uh, interact with the cosmic rays so that, for example, maybe shorter-lived particles survive for longer distances?
Oh, that's an interesting question. Yeah, in general, we don't really see very short-lived particles unless it's produced as an interaction in this air shower. But I'm not actually sure. I'm not actually sure about that. They're definitely relativistic. They're basically all just considered moving at the speed of light for all intents and purposes.
Um, One question is the neutrino energy related to the orb particle plot here in your um, diagram,
Mhm.
or is it shouldn't be the angle of neutrino energy be at lower energies regarding to the rest uh, energy of a particle.
So the neutrino, if these are, well, okay, if these neutrinos are produced at the same sources as these cosmic rays, we expect that the neutrino energy spectrum is reflection of the cosmic ray energy spectrum, because in this interaction, the cosmic ray, the neutrino will receive about 10% or so of the cosmic ray energy. So you would expect to see a correlation between neutrino energies and cosmic ray energies. And
Hmm.
indeed, you could say that maybe these neutrinos that are at about 10 to the 16 are coming from this population of cosmic rays a decade higher in energy.
Okay, thank you.
Can you talk about the radio emission, about how does it present itself? Is it all at once or is it dispersed across a frequency?
Yes. Let's see here. So the radio emission, um, yeah. So actually, it's quite complicated in the timing that it arrives at the ground. Um, so you have this interesting effect. Let's say you have an antenna like right at this position, where if you're on this preferred position in the radio footprint, this dark spot here, actually, radio emission from the entire air shower is arriving at the antenna at the same time. And this is this Cherenkov effect. And the reason that happens is because actually the particles in this air shower are moving faster than the radio waves. So if you emit a radio wave from, let's say, higher up here, it propagates towards your antenna, and then your particles are moving faster. And then so if you emit a radio wave down here, it can arrive at the same time as this one did. So that's kind of an interesting effect. Um, in general, though, what we see is that it kind of arrives as like a wave front because most of the emission is coming from this position of X max. So what you see is if you plotted, for example, the time of arrival of the signal in your antennas spread out over this entire footprint, it would look like yeah, like a spherical wavefront, basically. And it is spread out over quite a broad frequency band, and that's just because this signal is so impulsive.
And as it arrives, the full bandwidth is arriving together.
Yeah,
Okay.
yeah. So yeah, indeed, it's you could say that the position's a little bit outside the antenna. Sometimes, oh, sorry, have a little bit of spread here where you might get some lower frequency content towards the end of the pulse, but generally speaking, they're all impulsive signals. Yeah.
Katie, there's a question in the chat
Oh.
from Richard. Is it possible to detect cosmic rays through their ability to cause single event upsets in computers? Could you imagine a citizen science project like SETI at Home, where home computers and those in academia devote some of their time to record these single events in their processors and memories?
Oh, that's interesting. Actually, last summer I was on a plane and my computer stopped working, and when I brought it in, they thought it might have been a cosmic ray event. And I was making a presentation at the time on cosmic rays, so there's a lot of irony there. But that is interesting. You could maybe think about something like that. I don't know how correlated, uh, because it would be it's very chancy, right? Like you do have these situations where some kind of high energy particle is messing up computers. I don't know if you could correlate them all with the same event. I think you'd have to be quite lucky. One thing that I have heard of is an effort to use cell phone cameras to try to do citizen science. And the idea is that uh, I think the idea is that the cell phone camera should be able to see photons from an air shower. Um, and so maybe you could have, everybody like having their cameras on all the time searching for for flashes from air showers. That's an interesting citizen science idea. Yeah.
Um, just to pick up on that, somebody called Nick has just popped the word yes into the chat. Nick, are you would you like to pick up on that?
I was just replying to Richard's question earlier about the meteor beacon.
Oh, okay. Sorry, the crossed wires. My apologies.
In terms of the similar to the neutrino oscillations, which are observed as the deficit for the predicted neutrino production in the sun, is there like a similar effect from potentially galactic or extragalactic or sources of neutrino generation where the predicted type neutrino is then observed to exhibit at the observed point a similar deficit in terms of the oscillation from the initial neutrino produced?
Yeah. Let me see here. I'm looking for this one. Yeah, the tricky thing, well, I think that would indeed be, I don't know if you would say they're looking for a deficit, but you would definitely want to know the flavor of neutrino. With the solar neutrinos, where the deficit was very obvious, it was at kind of like the right distance for neutrino oscillations to occur. And I think over these extremely long distance scales, I think you would have complete mixing between the neutrino flavors, but I'm not a neutrino oscillation expert, so I'm not 100% sure about that. But people are trying to some different techniques basically uh, probe different types of neutrinos. So if I can actually go back here, IceCube can identify electron neutrinos because electron neutrino will interact, produce an electron, which kind of immediately decays or immediately creates like a puff, like a burst of a cascade in ice. This example here is a muon neutrino because a muon makes like a long track through the detector. And then a very interesting one is the tau neutrino. And this is tricky because yeah, it's an interesting observation mode because, for example, you could have a tau neutrino propagating through a mountain, and then a tau particle coming out of an interaction. Uh, and then that escaping and creating an immediate air shower because it would decay very fast. So if this was an electron neutrino and it produced an electron, the electron shower would get absorbed in the mountain. If it was a muon, it would produce a muon, which would escape and then continue without producing a shower. So there's some different techniques are trying to probe different types of neutrinos, which would indeed show a deficit, or even just knowing the relative amounts of the different flavors of neutrinos could tell you something about the oscillation lengths.
Katie, I have a question. You mentioned that for the lower energies, it's very difficult to determine any spatial information where the event is actually coming from. Do you see any developments in the instrumentation or the application of AI that might improve that situation?
Yeah, that's interesting. Actually, I think it's not so much sorry, let me just go out of here. I think it's not the instrumentation that is the problem because you can determine the arrival direction of cosmic rays very well to within, a degree or something like this. It's actually the knowledge of the Earth's the galactic magnetic field that is the problem point here. So,
Yeah.
yeah, I could imagine if we have better and better mappings of the galactic magnetic fields, that would go a long way towards being able to the better you know the magnetic field, the lower in energy you can actually start to do some pointing. So that would be really cool.
Does that work the other way round, that the cosmic rays can tell you about things about the galactic magnetic field?
Yeah, I guess if you knew for sure what a source was, um, then you could map the magnetic field with it. It's a bit of a chicken and an egg, but I could imagine I could imagine that you eventually become so sure, just due to maybe information about the primary mass and maybe some energetic arguments. You could say, okay, I know that I'm seeing a significant population of cosmic rays from Centaurus A. It's the only thing remotely in that direction that it could be true. We're not there yet, but that is something that is for like, maybe happens in the next decade. Then yeah, then I think you could actually map out the magnetic field of the galaxy.
Okay, there
With
are
the
a
gamma
couple.
ray observatories, how well can you detect gamma ray bursts,
Uh,
or can you?
with the ground-based gamma ray observatories.
Yeah.
I mean,
Is there?
if you're looking in the right direction, I think it should be fine. I don't totally. I have to be honest. I don't know exactly how high in energy gamma ray bursts are typically detected. The ground-based gamma ray observatories are usually looking at the higher end of things. But I think it shouldn't be a problem at all, except for that you have to be looking at the optimal direction, unless you have something like Hess, where you have the whole field of view. Sorry, Hawk, where you have the whole field of view.
There are a couple more questions in the chat. Take the second one first from Wendy. Is the mountain an actual site or a theoretical site?
I'd say it's somewhere in between. There are prototypes out there that are being developed. That particular experiment is called Grand Giant Radio Air Shower Neutrino Detector, I think is the acronym. And the idea was eventually to have 200,000 antennas there, which is like a huge logistical challenge, but people are actively working to make this reality. So they have a test site of, I think, a few tens of antennas there and a few other locations where they're kind of getting the technology going, I would say.
And the second question, in the ionizing particle observations of the central core of the air shower, has there been any observations of particularly of the heavy primaries?
Um, That's an interesting question. I don't think that we are sensitive enough at this moment to measure structure. Um, I do have very high hopes that with the SKA we will be able to do that just because let me see where it is here. Just because you get this incredible coverage of your radio footprint that you don't typically have. Usually observatories measure like maybe 10 points in this footprint. And at the SKA, we'll have the radio information of the entire footprint, but also with this particle detector array. Actually, one of my ideas is that we put particle detectors here that can distinguish between different types of particles, muons, and electrons, and that I think has the potential to really start to probe, small fluctuations in hadronic physics at the shower front.
Katie, when do you expect to get time on the SKA for this work? It's going to
Yeah.
be absolutely fascinating. We'll have to get you back.
Well, so this is also an interesting thing about, yeah, so the SKA, I think we're talking about a 5-year time scale, but I'm hoping that we can get some commissioning data earlier than that.
Are there any
Just
more
as a
questions? Sorry, yeah, Adrian.
Okay, sorry. Yeah, I was just going to give the information that kind of looked it up real quick. The highest energy detected from a gamma ray burst was 251 TeVs.
Oh, yeah, okay, so that's definitely in the range of ground-based detectors.
But that's atypical. That's the highest energy one that was detected on October 9th, 2022, and it was
Okay.
kind of like the record-breaking one.
I have one more too. Do these different stations communicate with each other? Is there like a radio telegram if there's a big shower event that's happening?
Yeah. For cosmic rays, we don't expect the events from different detectors to necessarily be coordinated because of this magnetic field scrambling. It takes them many, many light years to they don't go in a direct path. So we can't correlate cosmic ray events from the same sources, but it's definitely a thing for the gamma ray and neutrino observatories. They have all these networks where if one observatory sees something interesting, everybody else immediately starts looking.
Peter Lloyd has just put a question up. As regard neutrino detectors, have you heard of the work of Professor Joe Weber?
Um, I don't think so.
No. Peter, do you want to expand on that? No. It was just a question. Are there any more questions? Otherwise, we can we draw the session to a close. Katie, that was fantastic. Just we thank you for your for the time you put in sharing your work with the community here. I'm always impressed when academics take time out to share with us what they're doing, and so our hearts are full of gratitude, and we just thank you so much. That
Well,
was
I'm very glad people are
wonderful.
interested and I like talking about it. So thank you for having me.
Yeah, yeah, some great questions.
Mhm.
Okay, yeah, thanks again. And until December the 5th, we'll say good night and God bless. Bye bye, everybody.